Today we've got an exciting one for you, all about FME and reality capture data. So first of all, I'm going to go over a small introduction about reality capture and GIS, and then I will be passing over to Hamish Kingsbury, who will be doing a talk on FME and reality capture data, focusing primarily on LAS data. So reality capture and GIS, what's the relationship? This question comes up a lot because of similarities in the way that you use a lot of GIS servers to present the reality capture data. And in many ways, GIS has been evolving to do more of the capture as well. So there's been confusions occurring between reality capture and primarily remote sensing. When we talk about reality capture, we always talk about it as developing from traditional survey techniques, because traditional survey is all about precise measurement and measuring the world around us. Capturing reality is what survey is and has always been about. This diagram comes up a lot about UAV, LiDAR and laser scanning being a development of those traditional survey methods. And as this has been happening and technology has been impacting the traditional role of surveyors, there's been lots of talks about how surveyors are becoming the data managers, which is causing many tensions in people's organisations in the capture of this data. For example, between surveyors and engineers on the capture of precise data. But with surveyors becoming data managers, where does this leave the GIS analysts, who are the traditionally spoken to be the data managers themselves? And then we've got the IT people in the background trying to deal with all this large data. So perhaps there's another way that reality capture data has developed that we should think about a bit more as well, which is from remote sensing as well as traditional survey. So at the moment, we're doing a three-part series, which is going to focus on what are GIS capabilities with reality capture data, looking at FME, QGIS and Esri, and this is a three-part series. So we've got today's one, which is FME and reality capture by Hamish, and then we've got one on the 8th of November at 10:30, which will be Esri and Python and reality capture, and then we'll have another one which will likely focus on Esri, but we've got a few potential speakers for that on the 29th of November. So over to Hamish. Hamish's background is primarily GIS and spatial data. His first introduction to visualization and point clouds and LiDAR was through working in the GIS team for the NCTIR after the 2016 Kaikoura earthquake. Nowadays, Hamish works alongside a range of clients developing processes and tools to integrate systems and data using FME. FME can read and write hundreds of different formats, and this provides Hamish with capabilities to utilize a LiDAR-derived data alongside a variety of spatial and non-spatial data to provide fast and effective results for his clients. It's been very exciting seeing the preview of this presentation, and I'm sure you guys will enjoy. So now over to Hamish.
Excellent, excellent. So yeah, as Kirsty mentioned, I'm going to give a wee chat about FME and reality capture data and how I've used that in the line of work where I work in. So just before we kick off, I just thought I'd give a brief sort of agenda to what I'm hoping to cover in the next sort of 40-45 minutes this morning. So we'll start off with just some introductions, just primarily to the company I work for, Abley, and myself. Then I'm going to touch base on what exactly is FME and what does it do, and how do I use it, and what are some of the things that it can do. And then I'm going to touch on another set of tools called LAS tools, and as the name suggests, that deals primarily with LAS data. Then how can we utilize these two tools together, and what sort of processing can we do with this, and what results can we get out of it? And then I'm just going to show a couple of other examples around that's loosely related to the LAS stuff that I'll show beforehand, but around how we've utilized clashes within the 3D space, and also finishing up with some augmenting of traffic management. So I just thought I'd give a really quick overview into who Abley is and what we do. We've been around for about 10, 15 years now, and we started off as a transport planning and engineering company. And that's been the core focus of our business since day dot. And then that sort of does lead in quite well to that climate and sustainability sphere, where we work with a range of clients to develop and help ensure that they are managing their infrastructure and their transport requirements sustainably. And one of the big areas that we've had a lot of success in is road safety. So both here in New Zealand and over in Australia, but also North America and parts of Asia. Now, all of these three sort of areas, they have one thing in common, and that's all these things happen somewhere within space. You know, they've all got some sort of spatial component to them. So it was only natural that Abley sort of branched out into the location and the technology area, and to assist with that and to feed into that, also we have some relationships with some data providers that can feed data in and provide us with data to assist with these other spheres. So I sit primarily within the location technology and the data products space, and we've sort of turned that as our location intelligence part of the company. So location intelligence, what is that? At its core, it's sort of that fundamental GIS, the sort of discipline. You know, you've got your spatial data analysis, and you look at where the data fits, how it relates, what those relationships can mean, and how we can produce some results out of that. But we also do a bit of digital engineering, and that's sort of where my main focus is within that location intelligence sphere. We also do a bit of software development, again in the location area, and that helps us develop some location data products and services that we can offer to our clients. So part of working for a consultancy, of course, we partner with a range of other businesses and companies, and one that I'm sure a lot of you have probably heard of is a company called Esri, and they make the ArcGIS suite of GIS software, both at the desktop and enterprise level. And we also partner with a company called Safe Software, and they are they build and develop the FME suite of tools. On our data side of things, we partner with TomTom, and we use TomTom to get a lot of rich transport and sort of traffic data from their series of networks. And we also partner with HERE, and HERE has a really valuable resource that I'll be showing you today. They've basically got LiDAR for most state highways in New Zealand, and that's able to be purchased and analysed and used to develop tools and products and get results for clients. So, as I mentioned, we're obviously a consultancy, and that means we work with a huge range of different sort of areas. So primary industries, ports, roading authorities, so the likes of Waka Kotahi, local councils and the local roading authorities that go with them, central government, so Ministry for the Environment, MB, Stats, forestry sector, and utilities. So really, we work with a whole range of clients, and what we really focus on is being those problem solvers. So having someone come to us with a problem and us answering that. And that was sort of that sort of kicked off what I'm going to be talking about today. It wasn't a client, but it was an internal colleague, and he came to me and had this problem, and I worked with him to produce a solution, and this is what I'll be showing you today. So the last little bit of an introduction, just about me. Kirsty did a great job, so I'll be brief here. So my background is primarily geography and GIS, with a little bit of geology and a bit of computer science splattered in there. I also have a postgrad diploma in GIS, And I started with Abley back in 2014, and 8 years later, I'm still here. And sort of my core areas of focus is FME, obviously as I'm doing a chat about it today, bit of desktop development in Python, web development, and so ArcGIS Enterprise, and so that infrastructure level. And something that I really, really enjoy is problem solving. So being presented with a problem and then trying to use my skill set to resolve and produce a solution. So let's dive into talking about what FME is. Now, if we were doing this in person, I would ask everyone to throw their hand up if they've heard of what FME is, but because we're all sitting behind our desks, I'm not going to be able to see you all. But FME stands for Feature Manipulation Engine. Traditionally, it's been marketed as an ETL, or an extract, transform, and load tool. It's now sort of referred to as a data integration automation platform, just as it's evolved and the functionality within it has expanded to work with, basically work with the way that the world's moving now, with all these sort of remote pieces of software and requiring that big integration to pull information together and extract data out of that. So it was built by a Canadian company called Safe Software, and originally when it was built, I think 20, maybe even 25 years ago, it was built to manage forestry data, and it was built to read in this proprietary data format from the British Columbia Forestry Service and convert it into a more readable format. And then the founders of the company realized that, hey, this is actually a really valuable tool to have, so they expanded it. And what makes it really great to use is it's got a very data-centric model, so it focuses solely on the data. So once you read information into FME, whether it's from a CSV or a BIM model or a CAD document or a shapefile or really anything, it all exists within the tool in this one standardized format. So you can join information from a CSV to a shapefile and then join that to a CAD document and output that to ArcGIS Online or one of basically 350 formats. So it's really expansive in the range of functionality it has. And as I mentioned, it's not just a spatial tool. Whilst it sort of has a base in spatial information, it's evolved away from that. And probably most of the times that I use FME, I'm not actually dealing primarily in spatial data. And as we can all probably acknowledge, spatial data is really no different to any other data. Spatial data just has a location, an X, Y, or a lat long, or some sort of other reference in it. So FME it's got a user interface, and it's very modular, sort of like Lego blocks. So an individual Lego block represents what we call a transformer, and that is the transformer does one specific role. That could be create a new field or calculate a value in the field. It could be to test a value within the field and then filter it out. Could be to aggregate data down into a single row or a single feature. So like with Lego, you can have a pile of blocks, but you don't really start building something until you clip these blocks together in the certain way. And what's really cool about FME is that on this page, there's actually two examples of outputs produced by FME. Both that Lego blocks, so that was produced in FME, and you probably won't be able to see it, but on the little circles on top of the Lego bricks, instead of the Lego logo, it's actually the Safe Software logo. And the second is this Minecraft example on the left. So FME has the ability to write out to Minecraft. So this has taken a input from an IFC model and transformed it into a Minecraft model. So what does this sort of look like in reality? Well, it can look a lot of different things, just like Lego. If you give someone a pile of Lego and ask them to build a car, that car is going to look different to the car you'll build. It's going to look different to the car that your neighbour will build. But they'll still be a car. And FME, as you can see in this picture here, there's a lot of lines and it can begin to look like a spider web. But the fundamental is that data flows linearly through the process, and when it hits these blue boxes, which are the transformers, it does that. It does the task that transformer is set out to. And in this example here, we're taking an Excel document, and that's then transferring it or transforming it into something that can be imported into InfraWorks and visualized. So just to sort of give a really quick summary overview, as I mentioned, FME deals with data. Data is the core to FME, and it's not just spatial data, it's non-spatial data. It can read information from ArcGIS Online, from online services, and it can push that data back up into those services. It can do while it's reading in that information, it can do joining and aggregation, testing, and it can integrate external libraries such as Python or R to provide some extra, more specific processing steps. And then lastly, it can do this sort of automation step. And that can be as simple as converting a CSV, you put a CSV in a folder and output a shapefile, or to more complex workflows. And one workflow that where Abley and a lot of our clients have found really, really valuable is working or calling LIN's data service and pulling in parcel and title information. So that information on LINs changes pretty regularly. And for some of our clients, it's really important that they have up-to-date copies of this data that they can rely on, stored locally, to do analysis and visualization and to augment and benefit their systems. So we've got a process that will pull down the latest data from LINs, and it will then update the local data source, and this can happen hourly, daily, weekly, monthly, whatever frequency you sort of want to happen. And then it can also integrate with external pieces of software, so things like ArcGIS Online and also LAS tools, and I'm going to touch more on these two in a moment. So as the title of this topic suggests, as the title of this presentation suggests, it's sort of on reality capture data, and my foray, my sort of foot in the door to reality capture is in point clouds and LAS data. So what I thought I'd do is I went into FME and I searched all the transformers and searched for point cloud. And that returned over 40 specific point cloud processes. So these are processes that just work on point clouds. There's other transformers that can work on point clouds, but these ones are specific to point clouds. So this can be things like thinning a point cloud, building a surface from the point cloud, filtering out different components of the point cloud, merging point clouds together, really a whole range of different functionality. And these provide you with the ability to convert and analyze that, extract the data, and also then combine it with other formats. And of course, you want to be able to view the data you have. So here is an example in FME, and I'll show you this in person in a moment. This data was provided to me by Kirsty, and it's taken from a Leica RTC 360 unit, and this is 2 scans, and I believe it has about 22 million points in it. And as you can see, it's of a cul-de-sac, and we're picking up the road and the curbing, some vehicles, vegetation, and some overhead infrastructure. So I'll touch base on this a bit more, and this is one of the examples that I'm using, and you'll see how I can process that and some of the stuff I can extract from it. So LAS tools. What is LAS tools? I acknowledge that this might be a bit hard to see some of the lists in here, but this has been taken directly from the LAS Tools website. So LAS Tools is an open source, or LAS Tools has two sort of parts. So it has an open source free to use component where you can do some basic operations, but also has a licensed part where you can begin to do more complex analysis. And these are my words. These haven't been taken from their marketing materials or anything, but LAS Tools is incredibly efficient and very, very fast at processing data. It has the ability to be spread out over multi-cores, so the ability to utilize high performance machines. It does have a relatively basic user interface, but typically the way I use it is through the command line, and this allows me to programmatically call or make requests to LAS Tools to do things like clipping or thinning of point clouds through FME. And some of the things that you can do is like classify, tile, triangulate, generate contours, generate polygons from your LAS data. So what we're looking at here on the left is the point cloud of that cul-de-sac from the RTC 360 unit. And the way I've got it symbolized here is just with the classification. So ultimately, as it comes out of the unit, the data is not classified. However, by passing that through FME and LAS Tools, we're able to begin to extract some classification data out of that unclassified point cloud and identify things like ground and begin to identify overhead assets or buildings or vegetation. And focusing on the ground data that we can extract, because we've been able to do that, we can take a built-up area like this, scan it, and then begin to extract a DEM and an aerial image of that area without any of the surface, without any of the surface items on top of it. So how does this sort of work? And I will dive in and I will show the workbench, but just to give a good understanding, I've just got the wee sort of a workflow overview here. So of course, we need to read that data in. So reading it in, we do a bit of pre-processing just to make sure the data is relatively clean and is in a good state. And also for some larger areas, we split the point clouds down into more manageable chunks, just to make it a bit easier to process, a bit faster, because we can of course split that out over multiple processes within our machines. And once we've done that, we can begin to go through an automated classification process. And this is all done in LAS Tools, this classification, and it unfortunately is one of their closed source paid for components, but it contains what I can assume is some proprietary algorithms that they're able to remove noise from the point cloud, find which points are likely to be ground, calculate, then use that ground surface to calculate the height and begin to classify some of those other points into whether it's vegetation or a building or something like that. Then once we've sort of got that preliminary data, we're able to go in and begin to optimize it a bit more and make it a bit tidy and a bit better for consumption. So we produce a index and we compress that LAS file down. Now that we've got a really nice, clean, manageable LAS file, we're able to produce what I'm sort of terming as our secondary outputs. So we can produce a DEM and a DSM, RGB of both the ground, and if you say just flew a drone over the top, you'd still see all those above ground features. And then also the extents of the survey area. And then lastly, we need to of course finalize our outputs. Up to this point, everything's still split into those smaller blocks. So we tile that all up into a single output file and remove any temporary data. So as I sort of alluded to, these 3 steps in the middle, these are all done within LAS tools. But on either side of this is an FME process that packages all of this together and provides you this functionality within just the one tool. So now I'm just going to switch over to FME and show you what this looks like. So this looks like a really simple process, and ultimately it is. We've got reading in our information here on the left. We're just setting our coordinate system, and then we're calling LAS tools. And if we have a look at the information we need to set, a lot of it isn't really necessary for your day-to-day info or for your day-to-day running. But LAS tools has the ability to tailor its algorithms based on what sort of terrain type. And well, it might say wilderness and city and towns. I've actually found that sometimes it's a bit of trial and error. So I found that for this sort of residential area that Kirsty provided, Forest and Hills actually produced the best result. We can then go and specify, what level of outputs we want. So we want DSM, DEM, and RGB, and then just some fine tuning tools. So whilst that all looks nice and simple, if we actually dive into what this process is doing, we can see that it's actually quite a substantial process. And now I'm not going to go in depth into everything, but I will just quickly skim over it and show you some of these, show you sort of an insight into what FME looks like a bit more and how some of the transformers work. So on the left here is where we're reading in, or where the point cloud is coming in. And this is sort of our tidying up step, just our making sure that data conforms to what we're expecting. You can see here with our geometry filter that we're checking that the information coming in is actually a point cloud. Because this is obviously being built solely for point clouds, we can't really run it on a raster or something that we're not expecting. And then we've got our first sort of point cloud specific transformer. And the role of this one is to simply just extract the number of point clouds, the number of points within the point cloud. And for the example that Kirsty provided, that had about 23 million points in it. Next, we go and check, hey, is this a big point cloud? And I've sort of classified a big point cloud in inverted commas as 5 million points. And we tile it up so it's just a little bit more manageable and a bit nice to use. We then go through and we just save all this tiled information to a temporary location because we obviously need to reference this later on. And then once all that's saved, it's when we really start diving into some of our LAS tool components. So the very first thing we do is we filter out any noisy information within the point cloud. So as I mentioned, the way that I'm using LAS tools here is primarily through the command line. So what we're able to do is we're just able to create a relatively basic command line string. So what we're doing here is we're making a directory, and then we're calling the LAS noise tool. And this is, we're specifying the input file, the number of cores we want to use, and the function we want to do. And we want to remove what LAS tools determine as any noise. And this could be things like a bird flying overhead or a random point that has just been picked up that's floating in the middle of nowhere. Then once we've sort of cleaned up that, we can run into, or we start to step into some of our more hardcore, I suppose you could say, processing, where we would determine the ground, the height points are above ground, and then we try and classify any of those non-ground points. And an example, so just taking a step back, the purpose of this workbench when it was first built was to only extract ground information from a point cloud. So any of these classify the building or vegetation information that is classified isn't necessarily needed for what we use it for, but that doesn't mean it's not useful and can't be refined and better improved in the future. So we run our LAS tools, and after we've run these three steps, we have ultimately a classified point cloud. We then go through and we just do some tidyings up, and then we optimize it just to remove any excess data and to index it to make it nice and snappy. And then we begin to produce our secondary outputs. So we produce our boundary file. We then go through and we produce our raster outputs. So our DSM, our DEM, and our RGB values. And these are then called again in a very similar format, just using a command line string. And this gets passed through to LAS tools, and then we finish up and everything is sort of recombined, all the tiled rasters are pulled back together and the output is saved. So how do we process the data, and where have we used some of this? And I will have two demos to show you, but first just a couple of pictures and some other examples. So one place where we've used this is in conjunction with the HERE data of roads. So we've wanted to be able to extract the line markings from roads. So the first step we did was classify the point cloud and extract all the ground information, because we wanted to remove any vegetation, any overhead power lines or poles or vehicles or anything that might complicate the data more than it needs to be. And then once we had that, we were able to say, well, these points are ground, and then using the color value of the point, so the point cloud has been returned with the full RGB colors on it. We were able to convert those RGB values into HSV values. So hue, saturation, and value, I think it is. And that allowed us then to extract pixels, or extract points rather, that were yellow or white, or sort of within a known range. And from that, we were able to extract road markings. And we also tried this with extracting shoulders as well. And we had limited success where we were sort of looking at grey values. And it would pick up the whole road and the shoulder, but we weren't really able to then narrow that down to just the shoulder. Another place that we've used things like this is in visualizations. So I believe this is a video. So on the screen here, you can see a corridor design, and what you can probably see off to the sides is some stuff that looks remotely like point clouds. You can see lots of little dots. Now we used the ground classification tool for this, but we didn't keep the ground. We actually had a more reliable, not that the LiDAR data we had was unreliable, but we had a much higher accuracy and tested terrain that we wanted to use, but we also wanted to be able to see the assets alongside the road. So we used that point cloud information to augment that and to add extra value into the model. And another example of where we've used something like this is designing or costing out road construction. So Waka Kotahi was looking at a tool that they could estimate their costs around constructing new roads, and they just wanted a real ballpark figure. So we were able to take again that HERE data and extract what the cross-section of the road looked like at the current point. Then we were able to check that against a proposed design model, and along the corridor where these changes were required or were needed, we were able to calculate the total amount of volume removed from cutting, and then also calculate any fill. And then, where applicable, use anything that was cut away to fill in those areas requiring fill, and see whether fill needed to be exported from the site or whether fill needed to be imported because there was a shortage of it. And this was able to give a really rough cost estimate in a very efficient way. So onto a live example. So again, this is using the data provided by Kirsty. And what you can see here is this point cloud in its raw form in ArcGIS Pro. So it's a nice detailed point cloud. If you zoom in, you can begin to see, it's got good definition on the curve and channel there. However, if we just wanted to extract the ground information and we then say classify it by ground, we can see that, oh wow, everything is not classified. So we're going to have a tough time at just pulling out the surface. So we're then able to run this raw point cloud through that FME process that I showed before. And it took about 3 or 4 minutes to run through and classify these 22 million points and produce us an output. So skipping over here, this is the data after it has been through the LAS tools and FME process. So again, just looking at RGB. But now what we can do is we can view it as classified. We can see that all these brown points are what has been classified as ground. So you can see it's been able to identify, that this here is not ground, that is a car, and it's been able to sort of classify that out. And of course, you can see there are some areas where it hasn't been very successful in classifying, but that can be resolved with fine-tuning the model and working through and finding areas where improvements can be made. Now, if I switch back to the RGB view, we can actually, instead of visualizing, we can now filter out the non-ground points. We can see here, when it all loads, is that now we've got a scene with the car removed, and it's managed to capture some information under the car. It's managed to retain a lot of that detail in the curve and channel, and it's removed a lot of the vegetation around, or in fact, it's removed all of the above ground vegetation in the scene. Now, this is all well and good, having a nice 3D scene, but sometimes we do, not everyone has the ability to view point clouds like this, and some people might just want to view it in sort of in a raster-based format. So, as I mentioned, we can basically produce a aerial image of this scene. So this is with all the non-ground features removed. So you can see it's done an all right job with the car, and it's done. You can begin to see some of those sort of scan lines emanating out. But bearing in mind this raster that I've produced here, I believe is 1 centimetre pixel size. So if you say ramp that up to 5 centimetres, you might begin to see some of this banding removed. Now, of course, you can also produce an aerial with all the non-ground features on it as well. So you can see we've retained our overhead lines in the car. But because a point cloud is 3D in nature, we can, of course, also produce a DSM and a DEM of that area. again, both of these DEMs and DSMs are, I think these are 10 centimetres that I'll produce them in, but you could produce them in 1 centimetre accuracy as well. Now, viewing a DEM and a DSM in a flat 2D raster is only going to take you so far. So of course, you can then convert these into a scene, and we can begin to see there the fall on the road and the falling into the gutter. And of course, this is just the ground only. We can switch over to the surface model, but as you can imagine, that can look pretty nasty because we've got all those overhead power lines. So on to the next example, and this is using the HERE data. So this is vehicle mounted capture. I'm not sure on the specifics of the gear that they use, but the example here that I'm showing has just over 100 million points in it, and this is north of Wellington. So heading up to the Hutt Valley is just up here, and Wellington is down towards the south. And what you can see is this has been captured by a vehicle driving along the state highway here, and it's picked up all our overhead power lines and light poles. It's picked up the service station forecourt there. You can sort of see that it's obviously picked up vehicles traveling along with it, picked up things on the rail, and of course, with the nature of this part of Wellington, it's quite steep and there's a lot of vegetation on the side of the road. So, of course, just like the previous one, if we view this by the classification on the points, we can see that it's not really really that useful. It's all non-classified, and it's all we can't really differentiate or extract any features from it. So running this model through that same FME and LAS tool process, this took about 7 or 8 minutes for the 100 million points. But we got the exact same outputs from the previous one. So of course here is it with an RGB with our post classification. But now if I switch over to classification, we can see that it has begun to remove a lot of those non-ground roadside assets. So our median barriers have been pulled out, vehicles in the opposite lane, the service station forecourt, it's pulled out a lot of the features along the rail line, the overhead gantries, and then switching back to RGB and filtering to ground, we can of course see all of this without any of the overhead or the above ground features on it. And then, much like the previous example, we can of course convert all of this into some raster-based scenes. Now, as I mentioned, I'm viewing this in ArcGIS Pro, and not everyone has access to ArcGIS Pro. So something that we can do is we can publish this up to ArcGIS Online as well, and we could either do this through the likes of ArcGIS Pro, or that can also be automated through FME. So now what we have here is that exact same point cloud scene, and of course the mouse controls are different in ArcGIS Online. So we can see that now in the browser, we're flying around this point cloud scene, and we can, I believe we can filter, sorry, I don't really use ArcGIS Online much. I believe we can filter out here we go, we can have a look at classification, and we can of course see the classification of this point cloud, and there we go, and we can filter based on the class, and we can keep only our ground class features, and all of this is being done on the web. So you'd be able to essentially do this out in the field on a handheld device, a tablet or a mobile phone, or on a laptop computer or something. And then, this is still, dealing with 100 million points. So you can also publish up the raster-based outputs, and of course view that in AGOL and zoom around, and you'd be able to, if you had roadside asset information, you'd be able to place that on top of this and view what proposed designs or something might look like. So that finishes up my last two sort of live examples. Now I'm just going to talk about a couple other areas where we've used point clouds and sort of that augmented or that reality capture data and what applications we've used them for. So one example is vegetation encroachment on power lines. So I'm sure we can all sort of understand that if a tree touches a power line, we're not going to be in for a good time. We might lose power, might cause a fire, could cause damage to infrastructure, damage to people's property, and that wants to be resolved, or the risk wants to be mitigated as much as possible. So using LiDAR data that was provided to us by lines companies, we were able to look at what the proposed sway and sag of these lines would be, represented in this picture here by this little red buffer under wind conditions. And this would show really quickly where lines may intersect with trees and allow them to perform preventative maintenance and also identify areas that might not be a problem just yet, but in 10 years' time, they may begin to cause issues, so they can address them sooner rather than later. So using a combination of FME, some of the Autodesk tools, and LiDAR, we've been able to produce these high definition terrain models and highlight areas where these conflicts may occur. Of course, power lines aren't the only thing that moves. Trees can move, and sometimes trees fall over. So using those three tools that I mentioned previously and a combination of some machine learning, we were able to take high resolution aerial imagery and identify crowns of trees. Then augmenting that and using that to select appropriate areas in point clouds, we were able to calculate, hey, if this tree fell over, what's the likelihood that it's going to actually cross over or intersect, touch a power line? And again, you can see with these purple domes here, we were able to produce something like that and see whether that then would intersect with a power line should the tree fall over. And then you could also combine that with the sway and sag and say, hey, this is potentially going to be a real a dangerous scenario in a high wind event. And then sort of the last thing that we've done, this doesn't really have too much LiDAR stuff in it, but able to augment traffic management. So what you can see here are some screen grabs from a mobile phone, and the assets displayed in this, so the road cones and the road signs, they are all produced programmatically in FME through a data-driven process. So the CAD traffic management is ingested into FME, and that contains information about where signs need to be and where cones need to be. Then FME is able to produce those signs and cones, space them out in the appropriate manner, and place them within an augmented reality scene. So of course, this allows you to see what traffic management plans would look like before they are set up, but it also will allow you to audit existing traffic management. And then you can combine all of this, and you can actually put it in point cloud. So the one on the right here is, again, some point cloud data that we have augmented with the traffic management data from the traffic management TMPs. And this has been ingested into Unreal Engine and been able to produce 3D scenes. But of course, what we can also do is add this into a browser, and again, much like the ArcGIS Online example, have someone out in the field on their phone or tablet, play that, view what the scene would look like. So that really sums up my presentation for today. Just before I close off and hand back to Kirsty, just a couple of really quick closing remarks. So FME, as I hope you've learnt today, this morning, has an extensive set of tools to work with a huge range of data, and FME and LAS tools really do complement each other. And something that this doesn't necessarily only relate to what I've spoken about today, but you might be familiar with a piece of software, and I was really familiar with FME and had never heard of LAS tools before I started using it. But I found that LAS tools was a really competent, efficient system of dealing with LAS data, and ultimately it was much better at some of the things than FME was. So being able to find that right tool and use them together allows you to create really, really cool results for your clients. Don't be afraid to try something new. If I didn't give this LAS tools piece of software a go, I wouldn't have been able to produce what I produced today. And as I've come to sort of realise, reality capture data is so broad and it has so many different applications. You know, you might be working for a power company or working with a power company, and their use case of reality capture data is completely different to an engineer or a transport logistics company. But the information that we can capture can be really, really valuable. And that really sums it all up. Thank you so much for listening today. I hope you were able to learn something, and feel free to reach out to me if you've got any questions or anything. I'm more than happy to have a bit of a chat. Thank you, and over to you, Kirsty.
Brilliant, thank you for that, Hamish. It was very informative. I'm just going to share my screen now. You know when you can see that?
Yeah. Yep.
Awesome. So we've got quite a lot of questions there. I'm just going to start running through some of them, but I'm going to say this in advance, sorry, that we're not going to be able to cover all of them. So we've got this question twice. I'll read it out. It's twice from two different people, that is. So I'll read out one of them. I noted the way that you got FME to recognise the line markings by colour. Do you have any tools that can detect or be trained to detect features based on their geometric properties? For example, have a LAS file of a neighbourhood and train FME to detect what a roof is. I think this is similar to what you were getting at when you were talking about the curb extraction, but did you have any more to add on that?
Yeah, so something we've done as well is extract roadside signs. So look at be able to identify vertical features within a scene. Yeah, and really it's just a case of understanding the problem and having a go. I haven't done any roof extraction myself personally, but as I mentioned, I'm always keen for a problem, and there's always ways to solve any problem that you may come across.
Awesome. How long did it take to classify the point cloud provided by Kirsty, and what were the specifications of the computer used to do it?
So, yeah, it took about 3 to 4 minutes to process that point cloud, and that was running on my laptop. And saying that my laptop is relatively high spec. It's a Core i9 with, sorry, I can't quite, with, what's that, 16 threads, 32 gigs of RAM, with a NVIDIA RTX graphics card, not sure exactly what one, but mostly that process is CPU bound. So the big benefit that I found, or that I find with processors like this, is the number of cores, simply that ability to split out over multiple cores to process that. So having 16 cores certainly helps speed that up.
Sounds like you've got a bit of a beastly laptop there. Awesome. Another question. Sorry, just trying to read through some of these. You've been using ArcGIS to view the FME-derived point clouds. Is there any inbuilt viewing capacity for point cloud data within FME, or is this on the cards, if you know?
Yes, FME has sort of two sort of desktop applications. They've got the workbench where you author and build your process, but they've also got Inspector where you can visualize your data. FME Inspector is very rudimental by design. It's not built to replace a full-blown sort of GIS suite of softwares. So it has some pretty basic tools, so you can't do like selection or filtering in Inspector, but you can definitely view the data that you have.
Awesome. You showed several visualization platforms, Cesium, Unreal, and I think InfraWorks. This is me reading that. Do you have any platform preference for these platforms?
Great question. I don't really have a preference. I am not particularly familiar with the InfraWorks sort of side of things. That sits very strongly with one of my colleagues. I have a bit of experience in Cesium on the development side of things, so I have built a number of proof of concepts for clients around visualization and the web browser. But probably if I was given some data and I needed to visualize it quickly and rapidly, I would go to the ArcGIS platform, simply because that is what I know the best and has the tools that I know to use efficiently. Not saying it's the best, but yeah, there's so many options out there to do a lot of that.
And you put it into ArcGIS online when you save for the ArcGIS platform?
I'd probably initially just stay on the desktop, just because the way Esri works is that storing data like that on the cloud does consume credits. So there is a cost associated with that, whereas viewing it in your desktop environment, whilst you need to pay for a license, it's a lot quicker and easier to view because you don't need to upload it, wait for it to upload and process and all that sort of stuff.
Yeah, definitely.
Really, it really depends on the use case of what you're wanting to achieve out of your visualization of the data.
What would you say the main use cases would be for some of those platforms then?
So, if I take it back to FME, very much in that design process, you're going to, visualize the data whilst you're designing your workflow. Probably ArcGIS Desktop is very good for the local viewing and performing sort of out of the box sort of analysis. ArcGIS Online is a great platform for sharing widely across your own organisation and other organisations, and also sharing out into the field, through web. So, all those two scenes that I showed on ArcGIS Online, you would be able to open them up on a mobile device on a 4G, 5G connection and view that. And unfortunately, I can't really say much about InfraWorks. I have seen my colleagues produce some pretty awesome video animations out of InfraWorks. So if you're looking for something marketing like that, I think InfraWorks is a great tool for that. And then when you sort of look at the cesiums, if you're wanting to build a bespoke viewer that you're not wanting to be tied into a commercial platform, then Cesium and 3JS are a couple of really good examples.
Great, thank you. I'm just going to ask 2 more questions, and then if you want a question to be asked of Hamish or me, just send through to our email, info@globalsurvey.co.nz if we've missed one of your questions, and I'll make sure that we get that information from Hamish. So just 2 more. This one is it possible to convert a LAS point cloud to Esri scene without LAS tools, either in ArcGIS Pro or FME?
Definitely. LAS tools is just a really fast and efficient processing method, and it's a tool more for extracting information out of your data. But FME has the ability to do any conversions that you might have. Esri itself does have some limited capability to read in some LAS files. So it can read in LAS with an S, but it can't read in LAS with a Z, so it can't read in a compressed LAS file. But FME is able to convert those formats into either a scene package or directly into something else that the Esri suite can read.
Thanks. And just the last question is about rasterization. It's actually kind of a 2-part question. What is the file size of the 1 centimeter raster roughly produced from the RTC data?
Great question. I have it here. Let me find it. So for the DEMs and DSM, we're looking at about 60 megs, and for the TIFFs as well, the RGB TIFFs, it's looking about 60, 70 megs.
Yeah.
So of course it was quite a geographically small scene. I believe for the second example, they were quite a bit bigger.
I can't remember how big the files are that I actually gave you, but in terms of rasterizing and reducing the data sizes, that's really significant to being able to pass the data around, making it lighter.
Definitely. I think the input file you gave me was about 600 megs.
So the kind of follow-up to that question about the rasterization was the point cloud coordinated, which I don't think it was. And then did you have any issues with the coordinate system? Point cloud?
Yes, I did. I had to. So I think, as you alluded to, Kirsty, there was no coordinate system on that point cloud, so it came in at 0, 0. So what I was able to do is to get it to show up in ArcMap, is I basically artificially placed it somewhere in New Zealand. I think I placed it over Hagley Park here in Christchurch, and then I was able to view it in a proper coordinate system. Of course, I turned off the any base maps that would show it in Hagley Park, but yeah, and you're able to convert. So I believe the Nokia or the HERE data, comes in as, I think it's WebMercator. It's either WebMercator or WGS84. I can't exactly remember which. So something we do have to do, or we do to make it easier, is convert it into NZTM. And that can be done through FME or LAS tools, and I think even Esri can do that.
Fantastic. Well, thank you so much for your presentation. I certainly learned a lot. It was really interesting, especially seeing your specific examples there. So any more questions, please email us at Global Survey. So for next time, just a reminder that this is a 3-part series. So next time we'll be looking at reality capture and GIS, and it will be a forestry case study. So we'll be looking at LAS data in a Python and ArcGIS environment, and looking at some of the capabilities there for volumetric calculations of trees for the ETS carbon scheme, which sounds super interesting. That will be presented by Susana Gonzalez, a remote sensing team leader at Interpine. So as always, if you have any content ideas or feedback, please get in touch. Thank you.